Alright, so we are going to start with the Z transform in this lecture. So we saw that for some series signals, we cannot analyze them with continuous time Fourier transform. Like examples are ramp signal or e power 2t u of t, these kind of signals. That's why in order to overcome this limitation, we used Laplace transform. Similarly, for some dt signals, we cannot analyze them with discrete time Fourier transform. And that is why we are going to go with Z transform. So, Z transform is analogous to Laplace transform. So, to give you some examples of CT signals and DT signals, let's say for CT signals, the continuous Fourier time transform can be used for energy signals, continuous energy signals, continuous power signals. But the Laplace transform for continuous signals can be used for energy signals, power signals, neither energy nor power signals, only some in this category. Similarly, DT signals can also be used. DTFT can be used for energy and power signals in discrete time. But the Z transform can be used for energy discrete signals, power discrete signals, as well as neither energy nor power signals, only some. Again, similarly, Z transform is very analogous, very similar to Laplace transform, except Z transform is used for discrete representation of signals. Laplace is continuous and Z transform is discrete. Z transform is discrete. So, what Laplace transform is doing for continuous signals, Z transform does it for discrete time signals. So we can also say that Z transform is the discrete part of Laplace transform. Yeah. So this was the introduction to Z transform and Laplace transform. Now we will look at the analysis and synthesis equations of Z transform. Now what is an analysis and synthesis equation? So similarly, as we have seen in Laplace transform, let x of n be let x of n be the discrete time signal. Now we want to find the z transform for this discrete time signal, and that can be represented as, here x of z represents the z transform, and here z denotes the complex variable. So how is this transformation takes place? That is determined by the analysis equation. So we are going to say x of z equals to n is equal to minus infinity to infinity x of n z to the power minus n, and this is called the analysis equation of Z transform. So in this we can see that it goes from minus infinity to infinity. So this transformation, this Z transform is called bidirectional Z transform. Now if we want to talk about unidirectional Z transform, then it becomes like x of z equals summation n is equal to 0 to infinity x of n z to the power minus n. Now this is a unidirectional Z transform. Now we use this analysis equation, this equation right here, to get the Z transform, right? The process, we are applying the Z transform on a discrete signal to get the x of z. Alright, now transform means it has to be reversible. Like if we can transform one signal into its Z transform, the reverse should also be possible, right? And for that we have to write an equation again. That equation is called the synthesis equation. So since the transforms are reversible, like x of n can be converted to x of z by using Z transform. Similarly, x of z should also be converted to x of n by applying inverse Z transform. And this inverse Z transform is called synthesis equation. The equation representing the inverse Z transform is called synthesis equation. And the equation representing the Z transform is called analysis equation. So we will be able to convert x of z to x of n, and for that equation is given by
and this is the equation governing
the inverse Z transform or the analysis equation. Sorry, this is the synthesis equation. So these equations are the analysis and synthesis equations of Z transform, and the analysis equation is also called as the Z transform, the actual Z transform. The synthesis equation represents the inverse Z transform. So this was the introduction to Z transform, in which we saw that in Z transform there are some CT signals we cannot analyze with continuous Fourier time transform, and that's why we use Laplace. Similarly, there are some DT signals we cannot analyze with discrete time Fourier transform, and that's why we will use Z transform. And we saw examples like for CT signals, CTFT can be used for energy and power, but Laplace transform we can use a lot of signals including energy, power, and neither energy nor power signals, but only some certain signals. Similarly, for DT signals, we can use energy and power signals can be represented by using DTFT, but Z transform can be used for representing energy, power, and neither energy nor power. So Z transform is also called the discrete part of Laplace transform because it is the discrete representation. It is analogous to Laplace transform. And next we saw analysis and synthesis equations of Z transform, in which we saw, let us consider a x of n discrete time signal, and if we apply Z transform on it, we will get x of z, where z is a complex variable, and we have to define the Z transform. This is how Z transform is defined. And this is called the analysis equation of Z transform. And if we use minus infinity to infinity, then it's called bidirectional Z transform, or else 0 to infinity is called unidirectional Z transform. A transform is reversible, so if we can convert an x of n to x of z, we should also be able to convert x of z to x of n, and that is governed by the synthesis equation, and this is the synthesis equation, or else inverse Z transform. That's it for this lecture. See you in the next one.